three things which are important. There is tension, compression, moment, right? And then the third thing is torsion. Okay, when we think of torsion, we're typically thinking of some shaft which is subjected to a torque. Okay, you can also have a non-circular sections which is subject to tension and so torsion, and that will actually be part of this section too. So here, first we look at circular sections, and then we look at non-circular sections. So imagine a cylinder, a shaft. Okay, and that's the axis. And it's subjected to a torque. This is the torque. That's the length, say. And then this say that this is the radius of the cylinder. So in our analysis of this, what we'll do is there's a little bit of trick here. So let's say that that's the face, and say this is the center. Okay, so theta is the angle by which this shaft twists. And so what that will do is that will cause so this is where the shaft is initially, right? This is if you draw a line on the shaft, it's right there. But then when you torque it, this line will move to here, and that will correspond, and that angle says made, that angle is gamma along the length. You know what, let me just use capital L to be consistent with the book. So that is the other end. This is the initial, that's the final. So if you draw a line, it will look like that. Now let's, my gammas are so much like my R. Hold on. No, this will look like R. Let's just call that, and let's call this R. Hopefully it's distinguishable. My R's are not different from gamma. Okay, so let's say that this point is C, this final point is C prime. Actually, you know what? Let's just use rho. Okay, and then we can change that. Okay, now C prime is basically the arc length, right? And I can write the arc length in two ways. One is I could write it as rho times theta, right? Rho times theta is the arc length, C prime. But arc length can also come from L and gamma, because now L is the radius of the circle centered. Well, this is the center, and this, you can think of this as the length. So then that is L times gamma. And so when we're talking of torsion, we are typically looking at gamma, which is our point of the angle of interest. So gamma is rho theta divided by. So that's the first important formula, which is it tells you what's the twist of the shaft in terms of that angle theta there, the radius and the length. Now gamma max is R theta by L. So why did I put rho and L? Well, you could have concentric circles, and let's say this one of these circles is of radius rho, right? And that's why I have rho there. But if you want to find the maximum, you always put the maximum rho, and that's R. Okay, the second thing we want to know is we want to go from gamma, which is sort of like the analogous thing in the uniaxial world is the strain, right? Gamma is like the strain, but in the torsional world, is to find the shear stress. So the formula for shear stress, and this is like an empirical formula, is that the shear stress tau is the modulus of rigidity times the shear strain. So gamma is shear strain. G is modulus of rigidity. Tau is the shear stress. So now we can write tau as G times, so I'm going to sub in from here, rho theta divided by L. There's a question. R and rho are the same, right? No. Rho is radius from, so rho goes from 0 all the way to R. It just gives me a way to figure out the shear strain as I change rho. So it gives me the shear strain in different layers of the shaft. So tau is that. And then tau max is when I put max for R, because you see that it's directly proportional to rho. So G times R theta divided by L. So that's the other thing you want to know. I think theta is called the angle of twist. And it is the length of the cylinder or shaft. So what you notice is that tau divided by tau max is rho divided by R. So it basically varies linearly with the distance, right? The shear stress is 0 when R is 0, and then it goes linear. So what we can do is we can show it this way. So the formula is tau equals rho divided by R tau max. And so if you have a shaft and you try to draw rho, sorry, tau, then it will be 0 here, it will be max here. Then if you have a shaft with an annulus, so it's a, well, let me just draw it like so, the center, then what will happen is there'll be a max and there'll be a tau min. Tau min will not be equal to 0. So there is shear stress in the inside surface. What I'm going to do for that is look the cylinder, the cross section, take a small element which is at a distance of rho from the center, which is now the radius. The shear strain is going to be something like that. And this element has an area of dA. And of course, this thing is subjected to a torque T. Now, the torque, the total torque is going to be, so the torque basically induces shear strain. So if you think of it, if you have a surface and you hold it and you twist it, then that whole surface is going to develop a shear strain, a shear stress. And the torque is going to be the force times rho. Now you need to integrate that force over the complete area. So the force in this case is, the definition of force is shear stress times the area. This is the shear stress due to this elemental area, small area dA, times rho. Okay, so what we can do is write an expression for tau from our previous section. We showed that the maximum stress on the outer surface, and tau varies as linear function of rho, so we'll use that expression here. So tau is rho times tau max divided by the radius, okay, dA times rho. So I'm going to move tau max because that's going to be not dependent on any of the things here, times so divided by r integral rho square dA. Okay, so this integral is known as the polar moment of inertia. Polar. So we have tau equals tau max divided by r times j. And so tau max is t times r divided by j. Now we can also write the shear stress at any cross section r, knowing that it depends on tau max as a function of, so tau equals t times by j. So this is just using the relation between tau max, this one, tau and tau max into this formula. So those are the equations which relate shear stress tau with torque T. Okay, now what's J? J is something which will give you for a circular disk. It is, if you have a disk of radius r, then J is pi divided by 2 r raised to 4. If you had a disk or an annular cylinder with the radius RO as the outer radius and RR is the inner radius, then J is now going to be pi divided by 2 R0 raised to 4 minus RI raised to 4. Okay, so we also know that the shear strain is rho times theta divided by L. And we also found an expression for torque. Torque is, or tau is, T times rho divided by J. And so if you want to find what's the relation between theta and T, and that will become obvious later on why we need that, then we know that the shear stress is G times shear strain. And so just subbing in the values, T times rho divided by J equals G times gamma is rho times theta divided by L. And so the rho's cancel off.
With the theta next to the G rho.
G, this is with this one. This is
G rho theta over L. Is that what you have there? They're not there. Look at the bottom.
oh here, yeah. I just sub this value. And then for this one, I sub in this value.
You have to like pay attention just because it's like sometimes it feels like the gammas look a lot like R's.
Yeah, I'm sorry. Okay, so then we can write an expression for theta that is T times L divided by G times J. Okay, so many formulas here. So that's theta. The other formulas you want to remember are, and I just put all of them down right here. which we have already derived, by the way. Gamma equals rho theta divided by L, and tau equals T times rho divided by L, sorry, J.
L would be like the length of these like pillars, cylinders.
Length of the cylinder. Right. And I think that's all to it. It's just these three. And then you can find the max and all by just noticing this. I think these are the three essential formulas which you you need. Now, of course, you need to sub in rho equals R to get the maximum tau, and rho, and the same thing when you want to find maximum strain gamma. Okay, so let's see how to use all this into word problems. Okay, let's start. Here is the first problem. Okay, so we have a shaft which has an inner and outer diameter of 4 and 6 inches. The maximum shear stress, max, is 12 KSI. Find the maximum torque that can be transmitted by the shaft without failing. So this is one of the basic conceptual questions which just tests you on if you can apply the formula. What's the relation between torque T and tau max? And for that, we've written this down. Tau equals T times rho divided by J. That's the general formula. Now, we are given the maximum shear stress, so we need to sub in the maximum, the place where the maximum shear stress would occur would be on the outer surface. So we need to put rho equals the radius. And then now there are two things here, which is, one is you will have a stress on the inner surface, you would have a shear stress on the outer surface, and clearly the stress would be maximum on the outer surface, right? So if you drew the annulus and then showed the shear stress, it would be tau min here and tau max. So all I need to do is tau max will be equal to T times R. Let's give them names. Let's call this the outer diameter, inner diameter. So it's going to appear in the outer diameter. Or let me just call it, we just call RO to be the radius corresponding to the inner, and RI and RO to be the radius of the inner and outer. So T times RI divided by J. But J for a concentric cylinder or annulus is pi divided by 2 R raised to 4 for the outer, R raised to 4 for the inner, and that's about it. So this here RO is 6 divided by 2, which is 3. Ri is 4 divided by 2, which is 2. And then tau max is given. T is unknown. So it's just a matter of substitution. So tau max is 12. T is unknown. Ri is 2. Wait, this should be, my bad. It should be Ro, right? Not Ri. So 3 times pi divided by 2. So, solving for T, you get 408.4 kip inch. Okay, so that was pretty much straightforward, just a conceptual question. Here is a much slightly more involved question. Okay, let's read through the question. So shaft AB and CD are solid of diameter D. You can see here D. While shaft BC is a hollow of inner and outer diameters of 90 millimeters and 120 millimeters. So 120 and you can't see the 90 mm, but that's the inner diameter. The shaft assembly is subject to torques as shown. So different shafts are subject to different torques, as you can see from the figure. The maximum and minimum shear, so find the maximum and minimum shear stress in shaft BC. So this shaft, you need to find the stress on this shaft here, and the diameter D, if the allowable shear stress in shafts AB and CD are 65 MPa. Okay, clearly there is a torque involved, there will be a shear stress, and we are looking at the expressions for involving torque and shear, right? So let's just see how they might be related before we actually start plugging in values. So tau equals T times rho divided by J. That's the formula which we just derived. Now the minimum. So let's first, before we do minimum maximum, the outer diameter is 120 divided by 2, so it's 60, and the inner diameter is 45, right? And we use these. Okay, so the minimum, as we've seen from the figure I drew earlier, shear stress, concentric or a disk is going to occur in the inner diameter. So T times R inner divided by J. Now the J is given as pi divided by 2R outer raised to 4 minus R inner raised to 4. So that's pretty much the expression. And then the maximum will be T times RO pi divided by 2. Okay, so then we ask what are the unknowns? Well, the unknowns are tau min, tau max, Ri, Ro, all these are given. So the only thing we need here to solve for this is the torque, right? The torque is not directly given to us. We need to infer that from the diagram. So you can, just like free body diagrams for a beam, you can draw free body diagram for the shaft. So what you need to do is, we need to find the torque right here, right? So we cut the section at BC. So we will have the first shaft, A, then we would have the second shaft at B, and then since there's a cut, it'll be something like this. So the torque on A is 6 in the direction shown. So TA. So TA, which is 6. And then on B, there is same direction, TB, which is 40. And we want to find the torque here. So let's assume the direction for the torque. Now you could take it either way. You could just assume that it's counterclockwise. This is a torque on shaft BC, and it's unknown. So just like you do equilibrium of forces in the x direction, y direction, here what you do is you do an equilibrium of torques for the shaft, right? Assuming that nothing is accelerating, right? No, the system is static. Okay, now that's not given in the problem, but in this course, we're pretty much dealing with only static cases. So acceleration is 0. It can have non-zero velocity, but the acceleration should be 0 for the equation which I'm writing down to be valid. The sum of the torques should be 0. So we have TBC acting counterclockwise, so that's positive. TB acting counterclockwise, again positive, and then TA, which is also counterclockwise, positive. So TBC is unknown, TB is 6, and TB is 14, TA is 6 equals 0. So TBC is minus 20, which is just saying that the torque I assumed is not in the right direction. It's I assume counterclockwise, should be clockwise, given by the sign. Anyway, so the torque here is TBC is equal to 20 with the direction as shown. So this is the torque. So now all I need to do is sub in the value of, so this torque, which is 20, has to go in these equations, and I have the formula for the minimum and maximum shear stress. So tau min, after doing all the calculations, comes out to be 64.7 MPa, and tau max is 86.2 MPa. In other words, if you take the shaft piece, the maximum will occur on the outer edge, and the minimum will occur here. Okay, that's the finding the shear stress. So next is a design question. We need to find the diameter of the shaft AB, right? This D is unknown. Okay, so for that, what we're given the maximum allowable shear stress. It's 65 MPa. So we need to use that stress to find the diameter. So the second part, the D is unknown. Tau max is given to be as 65 MPa, and then we're looking at the shaft A. So I'll draw A. I'll do the same thing, same trick, cut the shaft between shafts A and B. So we have TA here, which is 6. And then we can see here clearly that TAB has to be clockwise. And I don't need to write the equation here. It's obvious it's going to be 6, but in the opposite direction. So the torque is AB equals 6. It's kilonewton meter. Okay, so now the question is, how do I go to D from 6 from all these things? Now for a circular shaft without any solid shaft, we know that the shear stress is 0 at the center and it goes to a maximum value at the edge. Tau max is here and tau is 0 here, right? So then if you write the formula for shear stress is T times rho divided by J. If you want to find the max, you put rho equals R, but R is D divided by 2, because this is the diameter, divided by J. Now for J for cylinder is pi D raised to pi divided by 2. It's actually pi divided by 2 R raised to 4, but R is D divided by 2. So D divided by 2 raised to 4. So we have tau max equals, I can cancel this with 3. Right, just moving things around. Turns out that D is 77.8 millimeters. It's just like a free body diagram. So think of it this way. You have a beam, you cut it, right? So then you'll have V and V. Okay, now to answer the question, we should get the same answer if we go the other way. And so other way of doing it is this way. So if you look at, what's the question here? So what we can do here is as following. We can take D, we can cut it right here, but go this way. Okay, maybe that's what you're hinting at. So we can do that. So let's do it this way. So the cut is here, and so this is I just go to put the value 6. That's 26 this way, and then on B it is 14 this way. So this is going to be, so 14, positive 14, because it's counterclockwise, minus 26 clockwise, and plus 6. And then this, let's assume that it is counterclockwise, tau AB. Should be equal to 0, and tau AB equals, what's the answer? 6, okay. Is it positive? Yeah. So that's, you can get the same answer going other way, because it's in equilibrium. If it was not, then no. Yeah, but good question. Just put it here. So but you notice that tau AB is this way, it's positive, counterclockwise, right? But if you see the way I got it here, it's clockwise. And that's because if one side is acting counterclockwise, it should be act clockwise, so that the sum of them, when you join it together, the sum is equal to 0. So it's just like exactly the same things on which are true for free body diagrams are true for shafts subject to tension.